So the story that I'm going to talk about in these lectures begins with the finite field, a problem called the finite field nikodem conjecture. This was considered to be a very hard problem until it was solved about 6 years ago, and the proof was 1 page long. And this new trick in the proof was to apply high-degree polynomials to a question that didn't seem like it had much to do with polynomials. So what I want to explore in these lectures is this new method, the things that have been done with it, some ideas of where it comes from, some things before, and we'll talk also a little philosophically about it. So to start, I'm going to show you this 1-page proof. So the finite field nikodem problem takes place in a finite field. So f sub q is the finite field with q elements. And then a nikodem set is a subset of fq to the n. And it has the property that it's nikodem. It has the property that if you take any point in the whole vector space, then there exists some line that contains this point. And so that the line except for the point is contained in the nikodem set. Let me draw a picture to illustrate what this definition means. So suppose we have some point x. Then it says there should be a line through x. And all of the other points of the line should be are in the nikodem set. So I'll color them in red. That applies to every point. So for example, this point also should have a line through it, and all the other points are in the nikodem set. Let's suppose, for the sake of argument, that our original point x was not in the set. Then this first line that I've drawn does not qualify. So there must be some other line through this point, and all of the points on it are in the nikodem set. That's true for each of the other points on this line L through x. So we get a whole lot of lines that all of the points on the line are in the set. And if we have any other point x2, which is not in the nikodem set, then through there we have all of these lines, and so on. As you start to play around with this, you get the feeling that the nikodem set needs to be quite large. It needs to be a lot of the points in the finite field. So the nikodem problem conjecture asks how big a nikodem set needs to be. And the conjecture was that it should be a definite fraction of the finite field. And this was proven by Dvir in 2007. OK. So I'm going to show you this proof. It uses a couple of key tools, which are simple facts about polynomials. And I want to kind of highlight them because we're going to use them all throughout the lecture series. So tools. The first tool is the parameter counting lemma, I call it. So it says that if S is a subset of Fn, then I can find a non-zero polynomial which vanishes on S, and with a bound on the degree. So let me explain to you how to do this. Bound on the degree is proportional to the nth root of the number of points in S. So let me give a name to this degree. D is, I take the biggest integer less than ns to the 1 over n. And I'm interested in polynomials of degree d. So polynomials of degree d on this space Fn. And I want to think about how they behave on the set S. So I consider the restriction map that takes each polynomial and restricts it to S. So I get a map to the space of functions on S with values in the field. This is a linear map between vector spaces. And what I want to prove is that the map has a non-trivial kernel. Because a non-trivial kernel exactly means a non-zero polynomial that vanishes at every point of S. Now, to check that this map has a non-trivial kernel, it suffices to check that the dimension of the domain is larger than the dimension of the range. Let's think about what the dimensions are. The dimension of the range is the number of points in S. And the dimension of the domain is d plus n choose n. I'll talk about that in a second, which is at least 1 over n factorial d to the n. Now, if you plug in the size of d into this this dimension is indeed bigger than that dimension. And that's the proof of the lemma. OK, let me talk about this for a second. The dimension of poly D. Poly D has an obvious basis, which is the monomials. So x1 to the d1 up to xn to the dn. And the degrees have to obey that their sum is at most capital D. And then it's an elementary combinatorics problem to count exactly how many ways there are of doing this. And that's the answer. But if we don't care about exactly how many ways, you can kind of see that we have n choices. And for each of them, we have approximately d options. So the answer should be roughly like d to the n up to constants. And that's what's important, and that we'll use. OK, so that's the first main tool. I call it the parameter counting lemma, the following more naive way of saying what we're doing. We're picking a degree d polynomial. That means we have this many parameters to play with. And if the number of parameters that we have to play with is larger than the number of conditions that we want to impose, then we can find a polynomial that meets our conditions. OK. The second main tool I call the vanishing lemma is just a very fundamental fact about polynomials, that if a polynomial vanishes too many times on a line, it has to vanish on the whole line. So if p is a degree d polynomial, and p vanishes at more than d points on a line L, then it must be that p restricted to L is identically 0. OK, so these are two fundamental facts about polynomials. And the point of the lecture series, in a way, is how surprisingly many cool and not so intuitive things you can prove by using these two basic tools. For example, let's prove the finite field nikodem conjecture. Proof of theorem. So suppose we have a small nikodem set. This is smaller than some dimensional constant times q to the n. Then you can use the parameter choosing lemma to find a low degree polynomial that vanishes on this set. So we get a non-zero polynomial p. P is 0 on the nikodem set. And the degree of p is less than q minus 1. In fact, if you plug this in to our formula, we would get something like q over 10. But q minus 1 is what we're going to need. Now, I claim that this polynomial vanishes at every point of the vector space. Here's why. Pick a point in the vector space. By definition, it lies in some good line L. And then p vanishes on L without x. L without x is in the nikodem set. L without x has q minus 1 points. And so by the vanishing lemma, p restricted to the line L is identically 0. In particular, p of x is 0, because x is in the line. OK, so we've now almost proved the nikodem theorem. We have a non-zero polynomial, and we just proved that it sorry, that should be a p. We've just proved that it vanishes at every point. OK, now this is not quite the vanishing at every point is not quite the definition of being 0. So at the end of the proof, there's an exercise. So if p of x is 0 for all x in fq to the n, and moreover, the degree of p is strictly less than q, then p is actually the 0 polynomial. This exercise is closely related to the vanishing lemma. And if n is 1, this is the vanishing lemma. And in higher dimensions, you can prove it by using the vanishing lemma inductively. It's not that difficult. OK, so given this exercise, we now have a contradiction. We had a non-zero polynomial. It vanished everywhere. It was the 0 polynomial. And that is the proof.
Just to make sure, by the degree of the polynomial, you mean degree? The maximal degree of any variable?
So the degree of a monomial is the sum of the degrees of the different variables.
Oh, okay.
So that's degree. However, it wouldn't matter that much. It would just affect the constants. OK. So this is the proof that I told you at the beginning was so surprising to people. Now I feel like, so now I hope you understand the proof. But maybe you don't understand why it was so surprising. So I wanted to talk a little bit about why this was shocking to people. So there are two angles to this. One angle is that I want to explain why where this question came from that might look a little arbitrary, as best I can in a short time. So this question is the finite field analog of an older and more famous question in Euclidean space. Let me explain that. So instead of a subset of fq to the n, we have the subset of a cube, 0, 1 to the n. And for every point in the cube, then there should be a line containing the point so that the line except for the point is in n. So this is the point. We have some line. And except for the point, this is all contained in the nikodem set. Then you can ask the same question, how big is a nikodem set? And Nikodem gave examples back in the 20s of sets that obey this axiom, but they have Lebesgue measure 0, which is a surprising and counterintuitive thing. But nevertheless, all the examples are big in the sense that their Hausdorff dimension is as big as possible. And so the Nikodem conjecture the Nikodem conjecture says that the Hausdorff dimension of a Euclidean Nikodem set is always equal to n, full Hausdorff dimension. OK, so there's a Euclidean problem which is analogous to the finite field problem that we just solved. And the Euclidean problem is still open and considered to be very hard and kind of famous. And it's still not probably clear, if you haven't seen it before, why this should be considered to be an important problem. Let me just say in a couple of minutes. So there's some important problems in Fourier analysis, especially the restriction problem that was posed by Eli Stein in the 60s, which are natural problems. They look more natural than this. And there's some estimates about Fourier integrals. They're kind of fundamental problems in Fourier analysis. And people realized that these problems about Fourier integrals are related to somewhat simpler looking geometry problems like this conjecture. And so a lot of interest got attached to this conjecture then. And it developed more meaning than it looks like it has on the surface. And then people worked a lot on the conjecture, and that was very hard. And so since we're stuck on that, we explored various related problems and cousin problems. And so, for example, Tom Wolfe proposed the finite field Nikodem conjecture, which was then solved by Dvir. So there was a period of time where it looked like all of these problems had the same core issue going on, and that this problem was plausibly as hard as these deep central problems in Fourier analysis. And then it was proven in a page. And so for a lot of people in the Fourier analysis community, this was a shock. OK, so that's a historical point of view about why we're surprised. But even looking inside of the proof, oh, yeah, I should have said Kakeya.
Since a lot of people seem to say that, call it that.
Yeah. OK, so there's another problem called the Kakeya problem. Thank you, Peter, which is a close cousin of the Nikodem problem. And they're both related to Fourier analysis. They're very similar. The Kakeya problem, for some reason, is more famous. But the proof of the Nikodem theorem with the polynomial method is cleaner, and it's easier. I think of it as being the main thing. So I've been promoting the Nikodem as an equal partner. So both versions are wide open in Euclidean space. Both versions are proven by Dvir in finite fields. OK, so that's one reason that people were surprised. All right. But another thing is that looking in the proof, it's a little surprising why you should introduce these polynomials. So it seems much more reasonable to start with the definition and take some point that's not in the set, and then you know there's a line, and then you know there are some other lines through it. And you keep working like this and talking all the time about lines, and try to build up enough lines to prove that the Nikodem set is large. This is what a reasonable person would do to try to solve the problem. And it seems to be very hard to solve the problem that way. But if you introduce polynomials, then for some reason, you write a page, and there it is. So another thing that's surprising is why the polynomials are playing an important role here. That's something I've been thinking about for several years. And I don't understand it as well as I wish I did. But over the course of the lecture series, I'll share everything that I've managed to understand. OK. So we have this one tricky proof. And now I want to talk about the impact of this method, about other things that have come out of it. And so one natural thing to try to do is to take this idea and try to attack this conjecture, or maybe the restriction conjecture, and so on. And unfortunately, very little progress has been made in that direction. But there's been some interesting progress in another direction, applying this to problems in combinatorics. So now I'm going to tell you about some problems in combinatorics where this method has been applied. And I can show you one proof, and then I'll state one theorem and give a sense of what kinds of problems we've been able to solve with this new technique. OK. So the finite field nikodem conjecture, if we want to, we can think of it as a combinatorial problem about finite sets of lines that are in finite fields. And the method has become very useful for all sorts of combinatorial problems about finite sets of lines in any field. And so here's the first example in the real field. So suppose that L is a set of L lines in R3. Then a joint, a point x in R3, is called a joint of L if x is contained in 3 lines with linearly independent directions. OK, so if those 3 lines were all in the plane of the blackboard, this point would not count as a joint. But if you tilt the dotted line out of the blackboard, that would be a joint. So the combinatorial question is, given L lines, what is the most joints that we can make? Let's do an example. So for example, suppose I take an S by S by S grid of points. And then my set of lines will be all of the axis parallel lines that go through these points. So in 2 dimensions, it would look like this. And in 3 dimensions, there would also be some points here. So each of the points in the grid lies in one line in each direction, so it becomes a joint. And so we have S cubed joints. And the number of lines in this configuration is 3 times S squared. So there's S squared lines going into the board and 2 other directions, which are similar. So you can see in this example that the number of joints goes approximately like the number of lines to the 3 halves. And the question about joints that goes from the early 90s and was open for 15 years or so is whether this L to the 3 halves is really accurate, or whether there could be many more joints. OK. The answer to the question is that the L to the 3 halves is really accurate. And it was proven by Netz, Katz, and myself around 2009. So the number of joints is bounded by, say, 100 L to the 3 halves. OK. So I'm going to show you the proof of this, which will involve these 2 same main tools. It's a very similar method. And the main step is what I call the unpopular line lemma. So it says that if L has capital J joints, then there's some line with not too many joints, so that L contains at most 3 J to the 1/3 joints. So for comparison, in this grid example that we just drew, there are J equals S cubed joints, and each line contains J to the 1/3 of them. So the unpopular line lemma says that there's always a line which is not much more popular than in this example. And using that, it's easy to prove that in total there cannot be significantly more joints than in this example. So the end of the proof, I'll just say quickly, is by induction on L, on the number of lines. So the number of joints is at most the joints that are on this unpopular line, plus the joints that come from the L minus 1 other lines. And by induction, we can say we know how many of those there are, 100 L minus 1 to the 3/2. And if you manipulate this, it just follows that the total number of joints is at most 100 L to the 3/2. And the bigger you make 100, the easier it is to see that this works. OK, so the heart of the matter is the unpopular line lemma, to prove that there's some line that has not too many joints on it. And I'm going to show you now the proof of that using, again, these two main tools. So the main tricky step is to mention high-degree polynomials at all. So the main tricky step I'll label with a star for you. It says that to let P be a non-zero polynomial which vanishes on the joints and which is of minimal degree among all the non-zero polynomials that vanish on the joints. It's not very clear a priori that this would be a good way to solve the problem. But if we do this and explore this polynomial a little bit, then we'll rapidly get the estimate. The first observation is that by the parameter counting lemma, the degree of this polynomial is at most 3j to the 1/3. Because there's some polynomial that vanishes on the j joints of degree 3j to the 1/3. And this is the minimal one, so it can be only less. And now I claim that there is some line in our set of lines with the property that p restricted to the line is not identically 0. I'll tell you why this is in a minute. So suppose there's this line where p is not identically 0. This is the unpopular line. The vanishing lemma implies that this line L contains at most 3j to the 1/3 joints. P vanishes at all the joints, and if it had any more joints, then it would have to vanish on the whole line. OK. So why doesn't this polynomial vanish on every line? Suppose it did. Let's think about what that would mean at a particular joint x, which lies in lines with directions v1, v2, and v3. So first I observe that the gradient of x, gradient of p at x, dot vi, vanishes, because that thing is the directional derivative of the polynomial p in the vi direction. The polynomial is identically 0 along that line. OK, but the vi are a basis. And so the only way that all of these dot products can vanish is if the gradient p of x is 0. This is for every joint x. So now we know that all of the partial derivatives vanish at all of the joints. Del jp of x is 0 for every j and for every x joint. OK. And that is very suspicious, because p was the smallest degree polynomial that vanished on all of the joints. And these polynomials, del j of p, vanish on all of the joints, and they have smaller degree. This basically is a contradiction. So if I compare star and this, it follows that del j of p is identically 0 for every j. And then p is a constant, which is not 0, and then we're rapidly. This is impossible. OK. OK, so this is another so this is an application in combinatorics with another one of these one-page proofs. People tried different things for about 15 years. And without the polynomial, again, it seems very hard to get in there. I'm going to also state probably the most famous application in combinatorics. And now the proof is more than a page, so I'm not going to be able to give it. But I'll tell you the problem, called the distinct distance problem in the plane. So P is a subset of the R2 with the Euclidean metric. And the distance set of P is the set of all of the distances between points P1 and P2 in the set P. And the question is, how small can this distance set be? So for example, if I arrange the points evenly in a line, then the size of d of p would be the number of points. Can we do significantly better than that? This question was raised by Erdos in the 40s, and he gave an interesting example which beats that. And the example is points in a square grid. So using some number theory, Erdos checked that in this example, the number of distances is like a constant times the number of points divided by the root of the logarithm. A little bit better than putting them in a line. And Erdos conjectured that this was basically the best arrangement in the sense that this was optimal up to constant factors. And people have been working on it since then. And recently, with the polynomial method, we've gotten
Put them in a box.
pretty close. What's that?
The finite set is a box.
It's a, yeah, I put a square grid. What am I saying wrong? It's a finite square grid. Yeah, yeah, it's a box. Thanks, Peter. Yeah. OK, so recently we've gotten pretty close to that. So in a paper of Nets, Katz, and myself, we proved that for any set, the number of distances is at least a constant size of the set over the logarithm, the size of the set. And it's based on an idea of Elikish and Sharir. So I thought at this point I would share a few thoughts about this problem and about this school of problems that we've been talking about. I wrote recently a survey article about this for a book about the mathematics of Paul Erdos. So I was thinking a little bit about Erdos. And Erdos started off in number theory, and he was interested in prime numbers. And something that I think made a big impression on him is that in the study of prime numbers, you have very elementary questions which are really difficult and deep. Now, one moral that you could draw from that is that prime numbers is a very special and unique field of mathematics in which there are elementary questions that are particularly deep. But I think Erdos ultimately drew a kind of opposite moral, that the prime numbers are not so unique, and found lots of other elementary to state really hard questions. I think it's exciting to try to find elementary to state questions that are hard. And the most exciting thing is to find an elementary question which is hard to solve and which is totally different from the previous list of elementary questions which are hard to solve. And when Erdos did this, I think is a good example of such a question. And people spent a lot of energy trying to understand what is hard about this question. What is the nature of the difficulty? What is the question all about?
I mean, I saw your co-author getting a prize. Didn't he put a lot of money on this one? For him?
He put some money, I think $500.
You did, yeah, you got your check.
I didn't. Well, it's not about the check.
I was at a lecture where the guy giving it, Ron Graham, was debating whether the log, whether you deserve the thing because of the log.
Right. We're getting close.
I can't for you.
Thank you. Yeah. Yeah.
Just to make sure, this problem is a natural generalized to any dimension, right? So you take two, you say 2 there, 3 here, and just a number. Is it really about 2?
Yeah, it's not so much about 2. So if we look at higher dimensions, you could put a higher dimensional grid. You then do much better than this. But so you have a good candidate, the higher dimensional grid, and you have a great problem, which is quite open. Is the higher dimensional grid the best? And joints also, you can go to higher dimensions. And in that case, nothing really changes. Yeah. So this was the beginning of a whole field of combinatorics, which is called incidence geometry. It's one of the first papers about it. A whole field developed to try to understand what is actually the issue in trying to prove that. And the subject of my third lecture will be incidence geometry. And I'll try to overview this whole field. and what are the successes and what are the obstacles and issues. OK. And then another little thing I wanted to say is I had to decide what is the center of my talks. And I was thinking a little bit of making this theorem the center of the talks. But I decided I'm more interested in making this polynomial method the center of the talks and talking about all the things that are connected to that. So it means I won't show the details of this proof, but I'll try to show what I think are the interesting ideas that are under the proof. OK. OK. So I want to come back to the issue of what all of these things have to do with polynomials. The first connection that I know about is to play around a little bit with different questions about how lines intersect in space. And at some moment, we'll see a very important example, which involves an algebraic surface. So let's start to play with this. And instead of asking this joints question, I ask the most naive question that I know how to ask. I have L lines in space, and how many intersection points can there be? So an intersection point is just a point that lies in two lines. It's so naive that I feel like I should call it question 0. So how many intersection points? OK. So the answer to this is L choose 2. There are at most L choose 2 intersection points because every 2 lines intersect in at most 1 point. And this can actually happen. To see that it can happen, it happens if all of the lines are in a plane. And within the plane, they're in general position. OK. So then I say, I understand. Lines can intersect a lot by clustering in planes. Lines like to cluster in planes. And so then we can probe this, and we can ask, suppose now I forbid the lines to cluster in planes. How much now can they intersect? So I'll call that question 1. So I think it's sort of the first real question. So let me forbid. I'll say there are at most 10 lines in any plane. Right. So now how many intersection points can there be? Is it still around L squared, or is it much fewer? And here there's a very important and simple example. So the answer is it's still around L squared. There's a very important and simple example that involves a degree 2 algebraic surface. So the surface I'll call S is defined by Z equals X times Y. And the important thing about this surface S is that it contains many lines. So it contains what I'll call horizontal lines, HA. This is the set of lines X, A times X. And it contains what I'll call vertical lines, B, Y, B times Y, Y and R. OK, let me draw a picture. So one point is you can check algebraically that this is a line as a function of x, and that it is in Z equals X times Y, and the same for that. So algebraically, we see that it contains all these lines. Geometrically, what's going on is that I think of my surface as a graph over the xy plane. So this is x and y. In the xy plane, I draw this grid of lines. And I think about the surface over this line, the graph over this line, and it's still a line. And so inside of the graph, also, there's a grid of horizontal and vertical lines looking like that. OK. And now to get a lot of intersections, I choose L over 2 horizontal lines. And I choose L over 2 vertical lines. And then I get L squared over 4 intersections. OK. So lines not only like to cluster in planes, they also like to cluster in certain degree 2 algebraic surfaces. And at this moment, degree 2 algebraic surfaces are a natural part of the story of how lines intersect in space. And so polynomials reasonably can be involved. Let's push a little bit further. Actually, you don't have to push very long. This is something I like about this field. You don't have to push very long before you get to the frontier. You go one more push, and we'll get to the edge of knowledge. So lines like to cluster in planes. They like to cluster in degree 2 surfaces. Let's forbid both of those things. So question 2, I still have my L lines at most 10 in any plane or degree 2 surface. What now? How many intersection points can there be? OK. So it turns out in this case that there is a significant change when we forbid these things. We don't know the full answer, but I'll put down partial results. So it was proven in the 90s that there are at most L to the 5/3. They don't quite write this, but by the methods of Chazelle et al., you can prove this. This was the paper that introduced the joints problem. And then more recently, it was proven that there's at most L to the 3/2. That was done by Katz and me. And it plays a role in the proof of the distinct distance problem. OK, so this is the best upper bound. And then we can look at examples. The only examples that I know, I tried a little bit, medium bit. The only examples that I know have around L intersection points. It's trivial to do this, right? Each time you add a line, you just have it intersect another line somewhere. And so anyway, so the truth is somewhere in there. OK. I want to make a few comments about what's going on here. So one point is, what is significant about L? We can get some perspective on what we're doing by counting parameters. Ever since I saw Zeev's proof, I've become more and more excited about getting intuition about things by counting parameters in a naive way. OK, so what are we choosing? We're choosing L lines. And so they're each. Yes, this uses the polynomial method. So this. It doesn't use the polynomial method in the sense of high-degree polynomials, parameter counting, and vanishing lemma. But it does use degree 2 polynomials. So they knew about this. And the properties of this kind of surface played an important role. So actually, without using polynomials at all, then it seems to be very hard to get started. So say on joints, there are a whole bunch of papers, and they get better and better bounds. Every one of them uses polynomials somewhere. And it's not clear that you need to use it. OK, anyway, so what's significant about L? We get a perspective by counting parameters. So if I want to describe a line, I can say that it has the form z is ai times x plus bi, and y is ci times x plus di. So I assume that they're not vertical, but it's not a serious issue. And then I have 4L real parameters. OK, now suppose I'm interested in whether the ith line and the jth line intersect. So the condition that that they intersect, that's equivalent to one equation, so a quadratic equation in these parameters. So if I want to have more than 4L intersections, it means I have more equations than parameters. So more than 4L intersections is overdetermined. And if I want to have more than L to the 1 plus epsilon intersections, then it's very overdetermined. So these kinds of things are not growing on trees. And there's some intuition that they should exist only because of some special structures. So far, the special structures that we've found are planes and degree 2 surfaces. And the moral of this question is, are there other special structures besides those in how lines intersect? OK. Now, another thing that you might have wondered when we put up this question is, maybe there's a fancy degree 3 surface instead of this degree 2 surface. Then we could do something similar with all of these lines in it. So let me make a little vocabulary of what we might be looking for. So definition, an algebraic surface, let's say, is doubly ruled. It's doubly ruled if each point is contained in two lines, which are contained in the surface. That was the crucial property of this surface S. Every point was in a horizontal and in a vertical line. So this is, there's a classification result that goes back to the 19th century that says what all of the doubly ruled surfaces are. Theorem. I don't actually know to whom to attribute it. I know through nets that Cayley and Salmon did a lot of work on ruled surfaces. So just ruled surface means that each point is in a line in the surface. They did a lot of work on ruled surfaces, or they probably knew this. So the theorem says that if Z contained in R3 is doubly ruled, then Z is one of the characters we've already met. So more precisely, Z is a finite union of planes and degree 2 surfaces. So this theorem says there is no degree 3 surface waiting in the wings to come in and play the role of this. It says a little bit more generally that there are no other algebraic examples that we have to worry about in this question. And what's left to worry about is that we have to worry about whether there are totally non-algebraic examples. So the way the proof of this goes is that we first prove that if there are a lot of intersections, then there is an algebraic structure. Then it's well modeled by a pretty low degree polynomial. And once it has an algebraic structure, then we can study that by appealing to some algebraic geometry and this kind of thing and prove that it's just planes and degree 2 surfaces. How this theorem is proven? So I think I won't talk about it during the lecture, but it's actually also sort of the polynomial method.
You also have to worry about those that are not double ruled.
Yeah, that's right. So you might also worry about a surface which is not doubly ruled but contains a large finite number of lines. But techniques related to ruled surfaces are relevant for that also.
If you take a cubic scroll with a infinitely many lines.
What's that?
The cubic ruled surface has infinitely many lines.
Yeah. So Enrico says that there's a cubic surface called the cubic scroll surface, which has infinitely many lines. So there are.
One parameter family instead of two parameters.
Yeah. So there are lots of singly ruled surfaces. Point lies in one line in the surface, say the cubic scroll. But there's only very few doubly ruled surfaces. Yeah. So singly ruled surfaces are something to worry about there, but they're not as dangerous because we don't have lines intersecting at every point. And what we're counting is intersecting lines, intersections of lines. OK. So to recap, we have some idea how to take care of very algebraic examples using this type of tool. And we're worried that there might be totally non-algebraic examples. And so in my mind, the heart of the matter is to prove that all of the examples have some algebraic structure. So I'll put here combinatorial structure implies polynomial or algebraic structure. This is the heart of the matter. We want to prove that all of the examples that have this combinatorial structure actually have some polynomial structure. OK. So zooming back a little bit to discuss this in general, what does it mean for a set of points or a set of lines to have some algebraic structure? So I like to think of it in terms of the degree of the set. So if X is a set in Rn, the degree of the set is the minimal degree of a polynomial that vanishes on the set. P is non-zero. So to get a little perspective, we've been talking about this all along. The parameter counting lemma says that the degree of a finite set X is bounded by the dimension times the number of points in X to the 1 over n. And I wasn't super careful about the sharp constant here, because in all my theorems, there are very non-sharp constants in so many places. But this is morally correct in the sense that that's right. So if I draw some number of random points, then the degree really will be like x to the 1 over n. And by contrast, there are, of course, special arrangements of points where the degree is much lower. Like if I take a hyperbola and I put a bunch of points on the hyperbola, the degree here is 2. And the dividing line is x to the 1 over n. So a bit arbitrarily, I'll say if x is in R3, and if the degree of x is smaller than 1 over 100 x to the 1/3, then that's some algebraic structure. This is definitely false for random sets of points of that size. So if we can prove that a set obeys an estimate like this, it means it has some highly non-generic algebraic structure. There's a similar story for sets of lines. So parameter counting prime, if L is a set of L lines in R3, then the degree of the union of these lines is at most 10 times L to the 1/2. And if we go significantly below L to the 1/2, that's a highly non-generic situation where the lines have algebraic structure. So now we have some context where I can explain a lemma, which is a bridge. Combinatorial structure implies algebraic structure.
So all these conjectures which you throw or can be formalized, that's if degree is smaller than some algebraic structure exists. Is it a formal statement? Is it a conjecture?
So somebody said it's a definition. It's a definition. So what I can say formally is, look at all of the arrangements of some number of points. A subset of them obey this condition. It's an algebraic subset, and it has a very high codimension in the space of all arrangements.
Put my question differently. What's the meaning of P dot C dot L dot?
Polynomial, parameter counting lemma.
Got it.
Yeah. OK, so now I can state a lemma, or maybe theorem, that says that if there's a lot of combinatorial structure, then there'll be some algebraic structure. So if we have L lines in R3, and if they have the combinatorial property that each line of L contains at least capital A intersection points, then the conclusion is that the degree of the set of lines is at most some constant L over A. So comparing this and this, there's a threshold. If A is just L to the 1/2, then this bound is vacuous because it's weaker than the bound that holds for just any set of lines. But if A is significantly more than L to the 1/2, then this gives a non-trivial bound. It says something that the lines have a property of high codimension in the space of all the arrangements of lines, so that they have some algebraic structure. So this lemma is responsible for this gap. So suppose we have around L to the 3/2 intersection points. It's morally not a big deal to assume that there's the same number on each line. So we have about L to the 1/2 points, intersection points per line. And there's a big constant here. So we have 1,000,000 L to the 1/2 intersection points per line. That is exactly enough to get the ball rolling and say that there's some algebraic structure. And if we try to go below this L to the 3/2, then we have to worry about totally non-algebraic examples, and we have no way of ruling them out. OK. So the last thing I wanted to do in this talk is to explain the idea of the proof of the degree reduction lemma, which is a third illustration of how the parameter counting lemma and the vanishing lemma work very well together as a team. And the idea of this proof, I call it the contagious vanishing argument. So we have a bunch of lines. And then we have this degree d, which is around L over A. And I want to find a degree d polynomial that vanishes on all of the lines. So by parameter counting, I can arrange that p vanishes at around d cubed points that I get to choose. And the way I'm going to choose the points is that I'll choose d plus 1 points each on a bunch of lines. So maybe on this line, on this line, and on this line. So in my picture, d will be 2. Now, I don't have enough points at my disposal to choose d plus 1 points on every line. But I have enough to do a bunch of lines. I do as much as I can. Now, by the vanishing lemma, p vanishes on these lines. So now I have this. And now what I'm hoping will happen is that the other lines intersect the red lines a lot. And as long as each other line intersects the red line d plus 1 times, then the vanishing, polynomial has to also vanish on that line. So the vanishing is sort of contagious in the sense that if you have a lot of contact with people who have vanishing, then you get vanishing also. Okay. So at least in the picture, everything is OK. So the proof reminds me of models in applied math of how diseases spread. So you have some population, and you write down who knows who. And then if people are each connected to a lot of other people, then a disease rapidly becomes an epidemic. And the combinatorial information that we have in this lemma is that each line knows a lot of other lines. And above this L to the 1/2 barrier, people know enough other people, lines know enough other lines to be well set up to have an epidemic of algebraic structure. OK. Let's stop there. Thank you for your attention.
Thank you very much for this great lecture. Questions?
Has anybody got any idea how to get rid of the log to the half? New main theorem?
Yeah, so the only hope I have about that, so the theorems are phrased like, prove that there are at most so-and-so of something. And there's some example that shows that the so-and-so is tight. But a striking thing in this field is that there are very, very few examples. There are not lots and lots of examples that show that this p over log of p to the 1/2 is sharp. There's one example. And nobody knows how to prove this kind of thing. But in all of these types of theorems, it appears to be a very rigid situation where if you have anywhere near the upper bound or lower bound, then there should be some very strong structure. And what would be a great breakthrough would be to actually prove something like that. And if we knew something like that, maybe we could get the log to the 1/2 because.
Let's say, from a naive point of view, why in some of the theorems you are sharp, like in the
Yeah.
So why a priori? You just have to do the proof.
Yeah, no, right, I can answer that. So Ellickish and Scherer contributed by transforming the problem. So you take the problem, you transform, you transform, you transform. And then you get some problems about lines in space, and you go back. Right? And somewhere one of those transformations is not completely tight. And the reason is, what we're counting is, so if there are very few distinct distances, then there are lots of pairs of points at the same distance. We're counting pairs of points at the same distance. And we have a sharp up to constant bound for that. And then when you go back from this to the number of distinct distances, there's a Cauchy-Schwarz, which would be tight if the number of points, number of pairs in each distance was evenly distributed. But it's not, and so we lose.
Does there is any reason why, like, for example, with current methods we cannot improve, or you believe that maybe with current methods we can improve, say, L to the 3/2 to L, or?
Yeah, I think it's a real barrier at L to the 3/2. I'm trying to popularize this problem. This is not. I would be surprised with current methods. I think this is something we need something new. Yeah.
What happens if you do what I would call the spreading out method to try and reduce these to finite field problems with the same formulations?
Could you say what is the spreading out method?
Well, you have a finite amount of data with some numbers, and all these numbers lie in a finitely generated ring, and you can reduce that ring modulo the maximal ideal, and now you have this data over a finite field.
Yeah, OK, I understand. Right. So suppose I want to study the distinct distance problem with 1,000,000 points. And then I do some reduction, and I have 1,000,000 points in some very large finite field. The problem is that we don't understand well at all the situation where we're in a finite field and we have the degree of the field is way bigger than the number of points.
So you're afraid of big Q.
We're afraid of big Q.
What is known about, say, rational distances? You want the distances to be rational numbers.
So what's the question?
You want to find you have points, and you want the maximum number of distances which are rational numbers.
So Enrico's question, I'm not going to know much about this, is you'd like to have many different distances which are all rational numbers.
Yeah. Very hard.
Good problem.
The problem has been considered, but very little is known. It leads quickly to some impossible quantum equations, but I don't know if the method can be used at all.
Yeah. So I don't know if this method can be used for that problem.
Other questions? Okay, so let's thank the speaker again for this lecture. And tomorrow, part 2.